Earlier we derived this equation, analytical IPR equation, which was derived from Darcy's law, and we assume steady state, we assumed vertical well, it's completed through the whole interval, and it's a cylindric draining from the center of a cylindrical region, is undersaturated, and is at steady state, meaning that at the boundary, at the external boundary RE, you have some mechanism that is keeping that pressure constant. So you need to have some mass influx into the volume. So we are going now to take this equation, and we're going to try to change it to take into account other cases which are not as ideal. And the first change we're going to make is we're going to look at the case where we have pseudo steady state. Okay, or PSS. And when I'm at that regime, if you remember, I say that at RE there is a no flow boundary. So this could be for many reasons. For example, I have a fault, I have a seal, I have some structural feature that causes that I have no flow. But actually it could be simply because there is interference between wells, between producers. Okay, for example, I have here one producer, I have another producer. And at this point, actually, there will be a no flow boundary, because all material from here will flow to this wellbore, all the other will flow to that wellbore, but at here exactly there will be a no flow boundary. And of course that might change, become smaller or bigger depending on the rates of each well, but that's a condition where I could have a pseudo steady state. So to derive that expression, we're going to do similar thing to what we did for the steady state, for this equation. If you remember, we took the Darcy equation and we were integrating one part on the geometry from wellbore radius to the radius at which I have reservoir pressure, and from flowing bottom hole pressure to reservoir pressure. Now, one trick we're going to make here, which is a bit pirate, also for pseudo steady state, we're going to assume, well, that I can take QO out of the integral. It's constant, the rate of oil at standard conditions. And we know actually in steady state we say, well, this is a good assumption that this value will be constant with radius. But in pseudo steady state, as I have no flow here, actually I should have some increase of the flow towards the wellbore, of the mass flow, okay, of this QO. But we will see this, even though it's a bit pirate derivation, actually works very well, and it gives you the same result that it as if you made like a more thorough derivation, okay, taking into account that this can vary with radius. So let's do that. Let's assume, make a blind eye on that, and then do that. So for pseudo steady state, the radius at which I find pressure equal to reservoir pressure is going to be at 0.47 RE. If you remember, for steady state was 0.61. So it's a significant difference, 47. And that causes actually that the ln of, I have 0.47 RE divided by RW. And that is actually equal to ln of RE divided by RW minus 0.75. You remember in the steady state case, we actually have 0.5. So the change, and remember we said this guy is around 7.5, is in that order of magnitude, or 8. Okay, so that means that actually this change between 0.75 or 0.5 is actually quite small. It's actually quite negligible. So that's the effect of the boundary. So then that means that for pseudo steady state, the equation, the change is very minor. Okay, actually the J is the KH divided by mu BO at average times the ln of RE RW minus 0.75. And I need the constant 18.68. Okay, so you see it's very minor, the change, and with that only change then I can account for the steady state. We did that trick here that we assume this Q was constant, but if we do the more thorough derivation, formal derivation, actually we get the same value. And this is a strategy we're going to use also for other cases, for the gas, dry gas, and for saturated oil. Now other modifications we can assume, we can say, well, what happens with and for that let's talk about the skin factor. Okay, the skin factor was a concept introduced in was in 1953, and there were two engineers from Shell, one called Hertz, with the last name Hertz, and also one called Antonius van Everdingen. Sorry for my Dutch. Okay, this was a Dutch mining engineer. Okay, they were from Shell, both working in Houston. And I think I have a picture here. Okay, this is Antonius. Again, he won a lot of prizes, became a very decorated person in SPE, and this was a publication where he describes first his approach. Okay, this was published in 1953. Okay, so the principle it's simple. We say, well, we have, if we are going to plot here from radius RW to radius RE, okay, we're going to plot pressure as we did before. So we have one condition which is, we saw is a bit like that, okay, and this is supposed to be well with no skin. Okay. But actually in the actual case we might have that the well might have actually a bigger, actually it might have a lower. So for this is for the same rate. Here I'm saying this is the same QO that is flowing out of the formation. Actually I need to have some PWF here that I'm going to call prime, is a well with no skin, but actually in the actual case I'm going to have something like this, okay, where we have a PWF which is actually lower. That means that I need to have a bigger drawdown to get the same rate. And that difference, this difference between the ideal and the actual, okay, this is the ideal, this one here with no skin, and this is the actual. This is with no skin, and this is with skin. This difference is the delta P of the skin. Yeah, and this we are going to see now why we're looking into this, but actually with skin we can capture a lot of phenomena that is happening close to the wellbore. We have, for example, formation damage induced during drilling. We have a lot of particles, a lot of solids that are being trapped in the near wellbore formation. We have, for example, was on purpose. We do gravel pack, we do sand control measures, we do fracking, we do perforation. So we do things here in the near wellbore formation that actually they cause that the well will be different from ideal, okay, with no skin. So that approach that was presented by Hertz and Everdingen, they say, well, this is the delta P of the skin, and now I want to put this one in a sort of a dimensionless way. Okay, and the way to do that, I can say, well, take some term from the IPR. Okay, take some term from the IPR to make it dimensionless. So I'm going to say this is equal to a dimensionless factor called S, the skin factor, and then I'm going to multiply times something that makes it dimension, that gives dimensions, that gives units. So this is going to be 18.68 times mu BO at average times QO divided by KH. Okay, and all of these units, this is going to give you in bar. So you see here is like we have divided the combination of skin. Okay, one which is a dimensionless factor. Okay, and then one something is a constant that actually has units of bar. Okay, and let's see if we define that, what do we get? So then we're going to make the two equations. So first one equation, assuming ideal. Okay, so we have PR minus PWF prime. Okay, if you remember, this was our J times QO. Okay, so this was QO times KH divided by mu BO. Sorry, the opposite. This was 18.68, right? 68 times mu BO at average times the ln of RE minus divided by RW minus 0.75. We're going to use here the pseudo steady state expression, and they're divided by KH. And I hope I didn't forget anything. So that's the ideal, and then we have that PWF prime minus PWF. This is the scheme, okay, which is going to be that factor called S, okay, that is dimensionless factor, then multiply times QO 18.68 mu BO average divided by KH, okay, which was coincidentally exactly that factor that we defined here. So when we have these two, then we can sum these two equations, and then we end up with this one cancels out, okay, the ideal, and then we have the actual drawdown, the actual pressure drop from the formation all the way to the bottom hole. And here we end up with QO 18.68 mu BO at average pressure divided by KH, and we end up with ln RE RW minus 0.75 plus S. Okay, and then with this one we can actually define a new J, a new productivity index, that will be KH divided by 18.68 mu BO at average ln RE RW 0.75 plus S. And as simple as that, we have found a way. You see, it's almost exactly the same as the equation we had with no skin, with no, that assumes that a lot of things are ideal, but only has this term, this additional term here. Okay, so this, we said this is due to the convergence. This one is due to the boundary, which is very small, and this is due to the scheme. Okay, this is kind of the near wellbore effect, near wellbore non-idealities. And how important is that? Well, we know this guy is supposed to be something maybe around 8. This guy is very small, it's like 10% of that. And the skin actually is going to be important depending on how big is it compared to 8. Okay, if it can be that if it's very small, then you don't care too much about skin. Okay, you don't need to even to calculate it. But if it's very important compared to 8, maybe it can be double, twice 8, then it's going to be dominating. It's going to be a factor in the equation that is going to make a big change on the J. There are other ways that I can, instead of using skin, there are other ways that I can simulate, or I can compute this non-efficiency, this non-ideality. Okay, so one of them is the flow efficiency. Other definitions, these are equivalent to skin. Okay, so I have a flow efficiency which is a EF, and this is this ratio PR minus PWF ideal divided by PR minus PWF real, and this was QO divided by J ideal divided QO divided by J real. So then then these two go away, and I end up with the actual J. And if you remember the ratio, really the difference between the two J's is almost, they are almost the same, except for S. Okay, they are almost the same except for S. And then if we remember, well, we can say that these are roughly equal to 7. Okay, then I can say this is 7, approximately 7 plus S. So this is another approximation. You can see in some places, some textbooks, that actually they use flow efficiency instead of skin, but now you know how to convert between the two definitions to skin. Flow efficiency, and we have another definition, is the apparent wellbore radius, and this is I can say that, well, if the ln RE RW plus S is going to be equal to ln of RE divided by an apparent wellbore radius. Okay, that means that it's like if the well didn't have the radius that it's supposed to have, but actually has something that can be bigger or can be smaller. Okay, and in that case I end up with the definition of the apparent wellbore radius, which is RW e to the minus S. Okay, and if S is positive, you see that means that there is should be lower than the ideal. Okay, that means that the wellbore should be very, very small. Okay, but if S is negative, that means actually that the wellbore is bigger than the ideal. So that means that I should have a higher, so the radius is actually higher than the physical radius. So just some comments here. So if S is greater than 0, this means that I have damage, okay, or less than ideal. Okay, remember that means that PWF prime minus PWF is positive. Then if S is equal to 0, that means that this is ideal. This is ideal. Okay, that means that simply this is ideal flow. And then if this S is less than 0, then this means that its productivity is more than ideal. This is usually is that I have done something to the well. It's not damage, but I have done something, maybe let's call it stimulation, okay, to get a productivity more than ideal. Okay, and the same thing follows if you start to look at the efficiency. Again, the efficiency, if S is negative, then that means that that the efficiency is going to be more than 1. Okay, or also the wellbore radius, if the skin is negative, that means that it's going to be bigger. Okay, but it applies, the same thing applies here. So what else do we need to, so far we have looked into pseudo steady state, we have looked into the skin factor to take into account that is not ideal. We might get a pressure drop due to some things. Okay, so what else can we include in the skin? Okay, there is also one thing that we can say is the drainage area shape. Okay, and this was, I think this was in 1965, and was another engineer from Shell called Daniel Dietz, and in this case it was working in the Netherlands. Let me see, I have here this, and he said, well, really you don't need necessarily to have a circular geometry, okay, depending on the boundaries you have in the reservoir, the structural boundaries you have, or depending on the number of producer injector you have around, you might have different shapes. Okay, so he came up with a way that you can actually include those non-idealities, okay, so those difference from the ideal case. So that's Daniel Dietz. This was around 65. This is the best picture I could get of him. Okay, and what he said, well, we can include the shape area. We can say that in our skin, okay, we can say that ln RE RW minus 0.75 plus S plus, now we have a skin due to area. This is the shape area skin. And that's because, well, if we can say that we have any area, we have any let's say area here of the seen from the top where we have a wellbore, we can say actually, well, that area we can always put it in terms of some equivalent external radius. Okay, so we can say this is pi RE squared, and we end up with RE equal to the square root of A divided by T. And we have that radius, so we can include that into this lower part of the productivity index. Okay, and let's see, he provides even in this paper some values, so we can say how important it is. And we said always that the effect of the boundary is sometimes not that important. So you see here this skin due to area, so you have 0, actually no deviation from the circular. You have a square, and then it's very small. Okay, remember you have 0.75, so that compared to 8 and 0.75 is very small, but for some cases it can be significant. This table is taken from the book of Golan and Whitson, okay, well performance. From Golan and Whitson. Okay, I think this is the second edition. So that's another way to include this non-ideality. Okay, other cases that can also be analyzed with skin is, for example, that can be modeled, okay, or represented with skin is, for example, is formation damage, okay, where we have due to drilling, and in this case S is typically greater than 0. We have also partial penetration, okay, when if we see from the side our reservoir, we actually don't complete through the whole interval, but we only complete part of it. Okay? And then the flow becomes not anymore, it's not, you have here some effect that the flow is not radial anymore, but actually we have some effect. And because it's flowing on part of it on the vertical direction, then you have some problem because the permeability the permeability vertical is usually much smaller than the horizontal permeability. Okay, so this in this case also you typically have the skin is greater than 0. You have also perforation. Okay, remember we sometimes drill the well. Okay, we set a pipe, the casing, production casing, then we cement it. Okay, and then we lower a gun, and then we make holes, and then we make these perforations. Okay, to get access from the inside of this production casing to the formation. Okay, so this is simply to also increase the area that that is flowing towards the well. Okay, but as you see here, I can have all kind of strange phenomena flow on this direction, for example. Okay, and also the perforation itself can cause some damage. Some damage can be caused to the formation because it's something that I'm sending a bullet through the formation, and then I can create some compaction of sand close to this, close to the perforation. Okay, in that case, I can also have a skin greater than 0. Okay, I can also have sand control. Okay, here typically also have greater than 0. And here typically I have, again, maybe my perforated wellbore. Yeah, but to avoid sand production, I put a lot of sand of different sizes. Okay, that they allow to filter, and they allow to keep the sand from the formation, from the reservoir there. Okay, they don't allow it to come into the wellbore, and that's sometimes necessary if depending on the formation, depending on the size of the sand that I have in the formation, depending on the production conditions that I have, then I need to have some sand control. Okay, and this can cause again another skin type effect. Okay, so this thing is the gravel pack. Okay, and this is perforated in this case, so here we may need the cement. I didn't paint everything here, but other things that can be also captured with skin are a wellbore inclination. Okay, maybe we're not doing exactly wells that are vertical, but actually they are tilted, they're inclined, so I can also include that. Close to that, I also have the anisotropy, permeability anisotropy. Okay, that the KB is usually much smaller than the KH. Okay, then other things that can give me, for example, a positive skin is acidizing. Try to do stimulation, and also fracking. Okay, in which for example, in this case, I simply to be able to propagate a bit longer these fracks or these perforations, then I can pressurize inside here, and then this is going to simply create fracks. Okay, and in these cases, typically I do that to make a skin less than 0. In the literature, there are many expressions for skin due to the different reasons that we described before. So for example, here you have, this is from chapter 3, which is restricted flow into the wellbore, from the book of well performance from Golan and Whitson. You see one expression taken from Bronze and Martin, on partial penetration, that you decide the skin is a function of different things. Okay? The total length of the interval, the horizontal permeability, the actual interval that you perforate, that you completed. Okay, so you have many different, and here you have a kind of a nice sketch of how is the flow with partial penetration. So you have many expressions for different conditions. So I just encourage you, if you want to know more, that you check this chapter on the book by Golan and Whitson. But also be careful always that when computing that term, remember that it might be that it's very small compared to other terms in the IPR, or actually doesn't contribute, doesn't change much the productivity index. So always be careful. It's necessary to compute it and necessary to calculate it, but it at the end might not be that important for the productivity of your well.